a little bit on announcements. First off, hope everybody had a good spring break, and that you are raring to go in terms of finishing out the last 4 weeks of the semester. So we actually don't have a lot left, not just in the semester, but in this class. After this exam, what we're going to do is we're going to finish out the discussion on beam deflection. We're going to into our two really big final topics of the first is the analysis of stress. And so what I mean by that is what happens when you have an object that isn't being twisted or just pulled or just bent or just sheared. What if you have multiple stresses happening all at once? How do you handle that? And the second big topic, which is going to be the topic of buckling. Buckling is a little different, but it happens in the real world and we have to assess it. In terms of housekeeping for in here, the attendance is up to date, obviously other than today. All the outstanding homework is graded, and hopefully you turned in your Exam 1 corrections assignment. What we're going to do today is we're going to discuss review of the second exam, which is Thursday. One final thing I will mention, or two other points I'll mention before we get right into this. So first, in regards to when we come back from the exam, so when we come back from the exam, we're going to get right up into beam deflections. I recorded a really short video, it's about 20 or 30 minutes on beam deflections. I really would hope that you watch that so that when we come back after the second exam, get raring to go in the world of beam deflections. Two, if you got your exam from me today, what that means is that it's probably been sitting in my office for about 2 or 3 weeks. When I get the second exam graded, if you could please come and grab that, I would really appreciate it. I'll send the grade reports out just like I did with exam 1, but I'm hoping to get that one graded pretty quickly. Okay, because my other class, I don't have any exams till the finals. This will be the only exam on my desk once we get this graded. Okay. So we're going to get into a discussion of the logistics for exam 2, and I'm going to have a brief discussion on unit conversions because that was a really big sticking point on the first exam, and it's going to show up on the second exam as well as probably the third exam. So I want to make sure that we're comfortable with this moving forward in this exam. Yes?
We'll get the exam on Thursday. Are we all going to spread out like we did last time?
I'm going to talk about that. And the short answer is I'm not sure that it's really needed since it's going to be closed book. But I'm going to talk about that. So let's get into that. Let's get into the logistics for the exam. Let's get into operating the exam and what have you. So again, we're going to do things a little different with this exam in the final. It's going to be closed book and closed notes because I want you to go through the process of preparing a formula sheet. I'm going to talk about the formula sheet here in a second. But again, we're going to do it just like we did last time in here. I design my exams the way I've always designed them. I don't design them to be time critical. And the format's going to be largely the same. There's going to be a series of short answer questions on the front, and then there's going to be, I'm going to tell you, there's 3 problems. There's 3 computational problems for the exam. You are allowed a calculator. You are, and I don't really care what calculator you bring as long as it doesn't have a Wi-Fi connection. You can bring whatever you want. I do highly suggest that you bring a straight edge, okay? I think a straight edge will help you in the construction of shear and moment diagrams, and that'll save you some time, okay? Let's talk about this formula sheet. So you can bring a formula sheet, it's an 8.5 by 11, both sides, I don't care. You can put whatever you want on it, okay? But there's the following stipulations. Number 1, make sure you have your name on it, because I am going to collect them afterwards, and so make sure you put your name. You can put it small and maybe in the top right corner. Just make sure that I can find whose is whose, because I'll give them back to you after the exam's graded. You do not need to copy down necessary property tables. And if not only is it in here, but it's on Blackboard, I want to show you, I'm actually giving you this on the exam. So not only am I going to give you, here, let me move that mouse cursor out of the way. So not only am I giving you this, all of the necessary section properties for a rectangle, but I am also going to give you this, okay? You're going to get this snippet of the table from the back that has all of the properties of wide flanges. So you're not going to need to copy that down onto your formula sheet. I'm telling you right off the bat, this is what I'm giving you. And I'll go ahead and give you another one. Notice how the only shape that I'm giving you is the moment of inertia of a rectangle. In other words, Any moment of inertia calculations that you need to perform on the exam, you will only need this, okay? No triangles or circles or anything like that. So I'm trying to make that part as easy on you as possible. In terms of remaining stuff on the formula sheets, one big thing is I don't want you to include any fully worked out problems. And what I mean by that is no numbers from specific problems on homeworks or the lectures. And I promise that's for you, not for me or trying to be stringent. There was a lot of instances on the first exam where the exam was open book and open notes, that what was happening is there were values on the exam that were sort of showing up out of nowhere. For example, there was a problem on the exam that had a 2x2 square bar, and a lot of people were saying that the area was 0.196 square inches. I'm like, where is that coming from? And the reason is that we did a lecture problem that was kind of close to that, and that was the area in the lecture problem. So a lot of people were just using that value, and I actually think it added more mistakes. So that's the reason why I say don't include any fully worked out like numerical problems with examples, because I actually think that'll hurt you on the exam. But the last thing is I do think the formula sheet needs to be prepared by you. Okay, what I mean by that is I don't care if you handwrite it. I don't care if you use a word processor. I don't care about that. What I think would be not in your benefit is if you just took the screenshots from Blackboard, copies, you did a screenshot, put them on an 8.5 by 11 and hit print. I don't think that would be a valuable exercise. I know you would probably have an adequate formula sheet in the space of about 5 minutes, but I don't think you would not engage in the process of actually making the formula sheet. And I think that process is important because by doing that, you're actually studying. Okay, and that's what I'm really interested in. Now, so to go to your question about the space, because the exam's closed book and closed notes, because really all you need is a calculator and a straight edge, I think we can probably do the exam constrained to the desks in the room. I don't think it'll be like last time where we'll have people out in the hallway because everybody had laptops and whatnot. So I think we can probably do that here in the room, okay? We'll deal with any problems, I guess, as they arise that day. In terms of the topics on the exam, let's talk about what's on the exam. So first off, geometric properties. Be able to compute the section properties of composite shapes. So I'm talking about centroids, moments of inertia, etc. You need to be able to compute support reactions in order to do, which is the construction of shear and moment diagrams. So you can't construct a shear and moment diagram without reactions, unless I give you the reactions, and I may or may not do that. So if I don't give you the support reactions, you need to be able to compute them. But the really big aspect is you do need to compute or construct shear and moment diagrams for flexural elements. And we're talking about concentrated forces, distributed forces. We're talking about pin, roller, and fixed supports. Pretty basic stuff in the realm of structural analysis. For you civil engineers next semester, when you take structural analysis, we really ramp it up just on that topic. But then again, it's a critical tool for civil engineers. Did I lose my clicker there? Okay. The remaining two topics on the exam are the two remaining stress formulas. That is for normal bending stresses and transverse shear stresses. So for normal bending stresses, make sure that you can understand the stress distribution in a beam and be able to compute the bending stresses in homogeneous beams and be able to compute the bending stresses in composite beams. So composite beams are made of more than one material. For transverse shear stresses, make sure that you can understand what the stress distribution looks like, and the big deal is be able to compute transverse shear stresses in rectangular cross sections. In other words, you're not going to be required to compute transverse shear stresses for triangular beams or I-beams or circular beams or anything like that. Only rectangular beams. So I'm restricting that again to try and make that a little easier for you. You all know that on the exam review slides, I tend to include a greatest hits of all the necessary formulas and equations to try and make studying a little easier for you. So here are, I would think, the relevant formulas and expressions for exam 2. First off, I'd say the parallel axis theorem is a big one. So the parallel axis theorem is what we use to compute the moment of inertia of any shape that is comprised of a series of simple shapes. So if I have a cross-section that is composed of rectangles and triangles and circles, oh my, I can compute the moment of inertia of that collected shape using this expression, the sum of I naught plus AD squared. I naught is the centroidal moment of inertia of each individual shape. A is the area of each simple shape. And then D is the distance from the centroid of the simple shape to the centroid of the entire region. And we determine the y bar, the centroid of the entire region, by just using sum of AY over sum of AM. We have a tabular format that we've used in multiple examples in order to determine the moment of inertia of a composite shape. And when I say composite shape in this regard, I mean like just something that's not just a simple rectangle, like channels or angles or I-beams or beams with holes in it, etc. I'm not talking about beams of two materials when I use the word composite here. Next, shear and moment diagrams. So all I include here on this is sort of the logic and the rules that we use. So for example, we understand the relationship between load and shear. So at a given point, the slope of the shear diagram is equal to the load on the beam at that point. And then between any 2 points, the change in shear is equal to the magnitude of load. Then we can draw a similar analogy between shear and moment. That at a given point, the slope of the moment diagram is equal to the shear, and between any 2 points, the change in moment is equal to the area of the shear diagram between those 2 points. What we had developed were rules for constructing shear and moment diagrams for concentrated loads, and then shear and moment diagrams for distributed loads. And for concentrated loads, we had sort of that stair-step pattern for the shear diagram, and then for the moment diagram, it was sort of that piecewise linear function where the slopes of the moment diagram were equal to the values on the shear diagram. For distributed loads, we have a linear shear diagram and then a quadratic moment diagram. And we use our sort of lot to a little or little to a lot analogy in regards to the slope because again, the slope of the moment diagram is equal to the shear. Our bending stress formula is probably the real new stuff on this exam. The other stuff, in some degree or another, we've seen. I mean, we've seen centroids and statics, we've seen shear and moment diagrams and statics, so what we did in here was sort of a crash course refresher, but this is the new stuff. So to compute normal bending stress, we use the expression sigma equals my over I, so m is the applied bending moment, I is the moment of inertia, and y is the distance from the centroid to the point in question. So I remember I did have somebody ask, well, like, how do you actually construct this? Well, it's just a line. That's the centroid, my over I. This is the y for this point. This is the y for this point. Just compute a stress, Distribution, we know that the maximum bending stress occurs at the top and the bottom, and so we tend to use this term C, which represents an extreme fiber distance, to relate the maximum bending stresses. So sigma max, we tend to say is MC over I. And if the section is symmetric, we can say that the stress on the top and bottom will be identical, and we can use this section modulus, M divided by S, to compute the maximum bending stresses. Now for transform sections, this is a little bit of a new slide, but I thought it kind of captured everything that's important for transform sections all in one slide. So first off, note the uses of a modular ratio. We tend to compute modular ratios as being bigger than 1. E divided by the smaller e, so the E for the stronger material, and E for the weaker material on the bottom. Now, in terms of transforming, we sort of have two options, okay? Let's consider a wooden beam reinforced by steel plates. So I'm saying a weak material reinforced by strong plates. We have two options. We can convert the plates into equivalent wood sections. Moments of inertia for either section. We'll get different moments of inertia, just point blank. But while the I values are different, the EI values are the same. And so that gets reflected in how we compute stresses. So if we transform everything to a weak material, the stress in the weak material is computed. The stress in the strong material we have to adjust by N. Similarly, for this option, the stress in the strong material is just my over I, but for the weak material, where here we multiply by N, here we're dividing by N. Okay? And so I thought that was kind of hopefully a simple but neat way of collecting this idea all into one slide. For shear stresses, VQ over IB, V and I are constants. B conceptually be a variable, but for rectangular beam, really changes for a rectangle is Q, and Q is the, if we're talking about a rectangle, it's the area of the section divided by the moment arm, the distance from the centroid of the beam to the centroid of the block that we're considering. Okay, now, I am going to open up the questions here in a little bit. I want you to sort of let this stew and marinate in your brains as you collect all this. But I got something I want to do on the side. I want to talk about unit conversions and dimensions. I think that during this course, and honestly, maybe this should have been something I did on day one, but I guess I had an assumption that this was stuff that you had seen in other classes, but I'll tell you, this was an area of great, well, let's just put it like this, there was a lot of trip-ups on the exam regarding this stuff, and this is usually pretty easy. I cover this not because I don't think you can do it, I know you can do it. I want to try and prevent simple mistakes and simple things that you need to do on the exam. Like what I don't want to have happen is I don't want you to have a problem with the unit conversions and it causes a greater confusion with just the exam in general. I want this to be the easy part, and so I want to cover this in a somewhat formal fashion. Now, if you're good with unit conversions and you're comfortable with this, I apologize that the next 10 minutes are maybe a little boring, but I want to make sure everybody's familiar with this, okay? Now, my motivation for you doing this is a perfect example, okay? We had earlier in the semester, okay? And this was when we were looking at axial loads. We had a steel bar that was subjected to a point load here at point C, and it was indeterminate. We need to determine the reactions and displacements, etc. And oftentimes in engineering, we deal in situations where the units are given in incompatible terms. This was a perfect example of it. We had the member lengths in feet. We had the cross-sectional area in inches, etc., right? I could have given you P is 2,500 pounds and E is 29,000 KSI. These are common things that engineers have to deal with all the time. Just about every that we use in this class assumes that the units are compatible, that they are dimensionally non-specific. And so it's the responsibility of you as the engineer or you as the analyst to convert the quantities into a usable unit system. And this was an area that really tripped a lot of people up on the first exam. Now, how we deal with this is to use unit conversions, okay? In other words, what we do is we use known unit equivalencies to express a quantity in desired terms. So a known equivalency would be something like 1 foot equals 12 inches, right? That's a true statement. 1 foot equals 12 inches. So 1 foot divided by 12 inches is 1. I'm not saying 1 divided by 12 equals 1. That's not the case. I'm saying 1 foot divided by 12 inches equals 1, okay? And so by multiplying a given term by these conversion factors, what we're doing is we're eliminating the undesired units and expressing a quantity in terms that we want to do, or that we want to use. Let's consider this. We had a problem very similar to this on the exam where you had to take a quantity that was in pounds per foot and convert it to kips per inch. A lot of people had issues with this, and so I want to make sure that we're comfortable with this. Okay? How do we convert 3,200 pounds per foot to so many kips per inch? Okay, well, we know the following. These are my unit equivalencies. I know that 1 foot equals 12 inches. I know that 1 kip equals 1,000 pounds. Okay, so the way that we do this is we usually set up the following table. So what I do is I have this sort of horizontal line, and I can draw that horizontal line as long as it needs to go, and I start out with my given quantity, 3,200 pounds on top and the foot on the bottom. This pounds per foot, that's a fraction, right? So pounds goes on the top, foots go on the bottom, all right? And what I want is I want kips per inch, okay? So let's start off with the pounds and kips. This is pounds to kips. So what I need to do is I need this quantity here, okay? Now I can put 1 kip and 1,000 pounds, or I can put 1,000 pounds. What I'm going to do is this. I'm going to put 1,000 pounds on the bottom, and I'm going to put 1 kip on the top. The reason for that, fraction, right? And I have a fraction, and I say 6x divided by 6. What happens to the 6's? In those terms, or in those in that order, such that the pounds cancel. And so, if I were to just carry this out, I would take 3,200 times 1, which that doesn't change anything, divided by 1,000. And 3,200 divided by I need to use another unit conversion. In this case, what I'm doing is I'm placing the foot on the top and the inches on the bottom, because I've got foot on the bottom, foot on the top. And there you go. What am I left with? I'm left with kips and inches. Kips and inches. So this is what I plug in my calculator. 3,200 times 1 times 1. So typically with unit conversions, you can ignore the ones. So 3,200 divided by 1,000 times 12, I get 0.2667 kips per inch. That's how you do that, okay? Is everybody comfortable with that? Because we're going to do some problems to make sure that everybody is comfortable with it. And I know if this seems like too simplistic for some of you, my apologies, but I don't want this to be a sticking point on the exam. I want you to feel very comfortable with this aspect of it, okay? Again, note that all we're doing is we're multiplying this by a form of 1. 1 kip over 1,000 pounds, that's 1. 1 foot over 12 inches, that's 1. All we're doing is doing that, but we're arranging it so that our undesired units cancel. That's all you're doing, okay? So for example, how would we convert the following moment? How would we convert 250 foot-pounds to 70-inch kips? Well, we say 250, and now we have to figure out where to put the foot and where to put the pounds. Foot-pounds is a multiplication, okay? So both of those would go on the top. So think of it as times feet times pounds. And then what am I going to do? I want inch kips, right? So we know that 1 foot is 12 inches. So what I'm going to do is I'm going to put the foot on the bottom and the inches on the top, so that and that cancels. So I get inch pounds if I were to just carry this out. But that's not what I want. I want inch kips. So I've got pounds on the top, put pounds on the bottom, 1 kip here, the pounds cancel. And then what am I doing in my calculator? I'm doing, let's see, 250 times 12 times 1 divided by 1 times 1,000. And that's going to result in inch kips. And so when you chuck that out, you get 250 times 12, which is 3,000. 3,000 divided by 1,000 is 3. So that's 3. Is everybody okay with that? Is that comfortable? I want to make sure that we're comfortable with this stuff. Has it been a while since you've done this? Like done it this way? I'm imagining that this is like bringing it back to chemistry, am I right? This is probably how you did this in chemistry. Well, this is how you do it in general. Now, for this one right here, I want to make sure that we're all comfortable with metric. So 963,000 kilopascals. And specifically what I'm interested in is the prefix. Now, as you get comfortable with prefixes, you can usually just go, okay, kilopascals to megapascals, I'm counting the decimal back 3 places, mega to giga, I'm counting back another 3. So you can probably look at it and just say, well, it's 0.963. But if you're uncomfortable with that, you can use your prefix definitions. For example, 1 kilopascal is 1,000 pascals. And then you could say 1 gigapascal is 10 to the 9th pascals. You guys just use the letter designators, the prefix designators, as they're defined right out of your textbook. And so you can take 963 multiplied by 1,000 divided by 10 to the 9th. And what you're going to get is 0.963. So yeah, ultimately what you're doing is you are, I can write that 3 a little better. So ultimately what you are doing is, decimal point, but if you're uncomfortable with how many ways you need to adjust it, just draw out your unit conversions, okay? Everybody comfortable with this? All right. Let's ratchet it up just a little bit, okay? Do I need to stay here for a sec? Okay. Let's ratchet it up a little bit. So let's convert the following volume, okay? So 1,500 cubic inches. Well, I know that there's 12 inches in a foot. So I'm done, right? No. If I have x cubed over x, assuming x is a number, let's not get into math land where we're dividing by 0, that just gives me x squared, right? So I'm not canceling the inches, I'm only canceling one of them, but there's 3 of them. So what I've got to do is I've got to do this 3 more times. Because I've got inches times inches times inches, which is inches cubed, that and leave me with foot cubed. And so when you check that out, you get 0.868. This one's a little tricky, okay? So I've got 576 PSI. I want to convert that to KSF, okay? And if any of you think who would care about geotech, that's not an uncommon expression of stress. And for you mechanical engineers, okay, I guess you're not going to use that very often. So, but yeah, okay. So what we're going to do is we're going to say 576 pounds, but then inches squared, right? Because that's what PSI is, pounds per square inch, okay? So if we want to convert to pounds, we'll say 1,000 pounds is 1 kip, and then we'll say 12 inches is 1 foot. But I got to do that one twice because there's inches squared. Notice I'm putting the pounds on the bottom, so the pounds and the pounds cancel, and I'm putting the inches on the top, so the inches and the inches cancel. So I've got pounds and a pounds canceling. I've got inches, inches, inches cancel. And so I'm left with kips per square feet. So 576 times 12 divided by 1,000, you end up getting something like 82.944. Is everybody, I'm serious. I want to make sure everybody's comfortable with this. Again, this was an area where a lot of people had some this to cause a problem on the other stuff, okay? Any questions? Now let me talk a little bit about some advice for the exam. Just about every quantity in engineering mechanics can be expressed with 2 base units. Whatever you choose for force, whatever you choose for length. For example, your deformation is in units of length. Your moment of inertia is in units of length to the 4th. Your stress is in terms of force per length squared. So if you choose a base unit for length and a base unit for force, everything else tends to go from that. My general advice is that unless it becomes evident based on the units that are given, typically what I think that you should strive to do is choose a unit system that results in as few unit conversions as possible to make your life a little easier. But in the absence of that, good choices for US units are kips and inches, and for SI units are kilonewtons and millimeters. And so these are going to be the resulting unit systems for given quantities. Like moments are going to be in inch kips, or stresses in KSI, or in SI, kilonewtons per or kilonewtons times millimeter, etc. Now, I really want everybody to pay attention to this. This is probably the most important slide or set of slides in this presentation about units. I've been a professor for a long time. These are the mistakes that I have seen related to units. First, just don't do them at all. Just don't perform unit conversions at all. I give you a problem on the exam, and I say that E is 5,000 KSI, I say that P is 5,000 pounds, and L is 13 feet, and you just use them. Those values are not consistent. You can certainly plug them into some equation, and it will give you a number, and the number won't make any sense, okay? So you need to look at these and go, okay, this is in kips, this is in pounds. I need to figure that out. Maybe turn this to 5 kips. Maybe turn this to inches, right? So now I've got kips and inches, okay? That is a big mistake that I've seen on exams. Just not do the unit conversions at all, okay? Another big mistake that I see all the time on student exams is to just skip writing the units at all. To just say, oh, E is 5,000, P is 5,000, L is 13. No, L isn't 13. L is 13 feet. Know that you might feel that like you're in a hurry and you don't have time to actually write out the letter I and the letter N or the letter F and the letter T, but that's important, okay? Numbers. However, you're going to miss out on the necessary context. And I'm telling you, if you take out the time to actually look at those units, it will reduce errors, okay? Now, calculator errors. You know, I tend to think that the simplest way of avoiding those is to just do your calculations twice so that you get the same answer. But they are going to happen. I think there's no way to really eliminate them. The other is not accounting for powers correctly. So, for example, 1 foot squared is 144 inches squared. It is not 12 inches squared. Okay. So making sure that you account for the powers correctly, that's another big mistake I've seen related to exams. Another common mistake is improperly conflating units. This is a really big one that I want to make sure everybody understands. Moments, for example, can be expressed in inch kips. Inch kips means inches times kips, not KSI. They're not the same thing, okay? KSI is a unit of stress. Inch kips is a unit of moment, okay? Just saying that a moment is KSI is going to lead to incorrect unit conversions down the road, which is going to lead to problems with units. Okay? Probably the 3 biggest sources of error for this is when students are dealing with moment, when they're dealing with stresses, and they're dealing with distributed loads. I can't tell you how many times I've seen a student, here's a beam with a distributed load, and they say it's 12 KSI. No, that's stress. That's not the same thing. Okay? So I want to make sure that we're clear on this. Which of these are valid units for stress? Is KSI valid? Yes. What about kilonewtons times millimeters? No. What about PSF? What about per inch? What about inch pounds? Gigapascals. There we go. What about kilograms per square meter? Kilograms is a mass, not a force. Pascals. PSI per foot. Foot squared. Square millimeter. There we go. So those are our appropriate units for stress. What about for moment? Is KSI? First off, here's something to note. That isn't going to work. This is the same table. So the units that were valid for stress are not valid for moment, right? What about kilonewtons times millimeters? This first one right there, is that good? Per inches? No. Inch pounds? Kilograms times square meters? Kips times square feet? Newtons per millimeter. So these are the only two. So what's maybe a valid question for you to look at, and these slides are on Blackboard, were any of those, maybe a third or a fourth question is, that don't apply anywhere, right? Because some of them don't really apply to any of the units or the terms that we've looked at so far. Okay? All right. My apologies if for some of you that was kind of boring, but I think that was necessary to go through. Before we move on, does anybody have any questions about unit conversions? Is everybody okay with this? I'll post this to YouTube quickly. I ought to try and pick a few problems that we've done and make sure you're comfortable with the unit conversions. Okay, one final thing, and then I'll shut up and turn it over to you. If you check the Teams channel, I have posted some problems, some representative problems out of the textbook. If you can do those problems, I think you're going to be fine on the exam. So yeah. Now I'm going to shut up, turn it over to you. Any questions about the second exam? I know there's got to be some. A lot of people in here are thinking about the wonderful world of thermo right now. For an example, so. All right, hold on now, come on. Exam 2 land in Engineering 216. There's got to be some questions, come on. You feeling nervous about it? Feeling good about it? If you are feeling nervous about what? Like, we can talk about it, we got plenty of time. Everybody's quiet. What? No, I picked it up. I picked up what was going on. I did. Was that just a lot of information for 8 o'clock in the morning? Is that what it was? The effects of the margaritas and Mai Tais from spring break is still lingering.
You still haven't went to get margaritas, Lou.
No, I haven't. I have not gotten margaritas with my students. To make sure it's crystal clear on the recording that's going on YouTube here. Work like that, Mr. Hutchison.
Should be honored with.
What's that?
Should be honored with.
Oh, yeah. No, I appreciate the invite. I'm gonna have to respectfully decline, but I appreciate the invite. Staple it together, okay, that's fine. That's fine. I've had students, that's fine, I don't worry about that.
You're not picky about what type of paper we use?
I said 8.5 by 11.
I didn't hear you units.
That's.
Where's your units?
Now you're learning, now you're learning.
8.5 what?
Complicated, like the stress diagram, like the flexural stresses and composite beams. Are we going to be expected to draw like complicated ones?
No,
Okay.
I'll go ahead and tell you, no. But that being said, some degree of diagram construction is something I would expect. Because at a minimum, they're shear and moment diagrams. That some of the shear and moment diagrams that we've had to construct, just from a matter of the picture that you have to draw, are more complicated than any of the stress distribution. But am I going to make you, let me just, so the short answer is no, but let me say this. I again use a rule of three, I only have, in my opinion, a limited amount of time to test you on the wide variety of materials on this exam, and I have never found that it is beneficial to see how much heat can be generated from the friction between your pencil and the paper. I don't find that a valuable exercise of the exam, nor do I think it's representative of what you do as engineers. Yeah, you're going to have deadlines, but it doesn't work like that in the real world. And here's what happens when it does work like that in the real world. You get Samsung Note 7s,
Man, you ever blow up a lithium battery in your house? We did that a couple of years.
Oh my goodness. No, I haven't. Yes.
Could you kind of go
Y value for normal bending stress. So let's use a simple example, okay? So we'll say Y value for bending stress. So the first thing that I think that we need is we need a beam that is, I guess, representative of something that's complicated. Like I don't think a rectangle is going to be good enough. Okay, so let's use a triangular beam. Okay, interesting. Let's use some funky moments. So M is, I'm making these values up, 82 foot kips. Let's make it 82 foot kips. Let's say the beam is 14 inches tall and 5 inches wide. Now again, while we're not going to have triangular beams on the exam, I actually think this problem is healthy from a review standpoint, okay? So what we're going to do is we're going to explore sigma equals my over I, okay? We're not only going to draw the stress profile, but we're going to pick some points in between and see what y is, okay? Now the first thing that I want to make sure that we're clear about is, do we all know that for this triangle where the centroid is? If I have a triangle that's h tall, how do I get from up do I go? H over 3, right? So if the centroid is right here, hold on, I want to see something. Let's try this, see if I can. Oh. Let's see if I can make this pretty, because it's, hey, that's better than this.
I like yours better.
That makes one of us. What I mean, it's South Bend. Okay. Centroid, and this dimension right here is going to be 14 inches over 3, which is what? I don't have my, I do. So it's, what, 4.67? Or equivalent. Thank you. 4.67 inches, okay? So what I'm going to do is I'm going to draw a line extending from the centroid? I will put the centroid right there. With me so far? Okay, so the first thing to keep in mind is that bending stresses at the centroid are zero. Okay, just point blank, they are zero. Are going to be our bending stresses. Let's move this all down some so that we can all kind of see what's going on. Okay. All right. Now, I propose what the bending stress profile is going to look like is a line that crosses the centroid right here. So let's just imagine you had a ruler, and what is this going to look like? So it's going to look something like this. Oh. See, why does this keep popping up? Something about like that, right? So here are the bending stresses here. Here are the bending stresses here. Okay? So it goes through the centroid. Okay? So what we'll do is let's label some things. So right here, stress is 0. Okay? Now right here, this is sigma max for the bottom, and this is sigma max for the top. Okay? But we're also going to make it, okay? And I'm going to ask for the stress right here. So we're going to call this sigma gray. And where is that? Well, let's see. So the beam, we said, is 14 inches from the top. We'll say that I want to know the stress right here, where that's halfway up. So sigma Greg is at h/2. I put my name there just because I asked the question. All right. The first thing that we're going to ask for is the moment of inertia. Now, the moment of inertia for a triangle, if I remember correctly, was bh cubed over 36. Was that right? I think that's what we had used in a previous example. Let's make sure that I am correct on that. And the way that I am correct is because I have my textbook with me, which of course everybody has their textbook with them, right? Everybody's shaking their head. Yeah, sure. Yeah, bh cubed over 36. So this is 5 times 14 cubed over 36. Is that right? Not, dude. All right, the letter N. So that I know that my answer is what? Inches to the fourth. So what is 5 times 14 cubed divided by 36?
381.11.
381.11 inches to the fourth. Do I have a second on that? Is that just like emotional support, or is that? M was 82 foot kips. Sure. Now, let's say that I want my stresses in PSI. If I want my stresses in PSI, this needs to be some quantity in inch pounds. Remember, a moment is a force times a length. So if I want stresses in PSI, I need force times the length, pounds times inches, or inches times pounds. So, 82 foot kips. So, 1 foot, 12 inches. 1 kip, 1,000 pounds. This is going to be a big number. What is that? $984,000 inch pounds. Okay, so what's the expression that we're exploring again? What was it? It was sigma equals my over I. That's what we're exploring. So we know what m is, and we know what I is. And notice how we have already accounted for unit inconsistencies. We've already taken care of it. So the only thing left is y, which is the purpose of this question. Remember, what is y defined as? It is defined as the distance from the centroid to the point in question. Okay? So let's start off with the easy one. What is the value of y here? That out. H over 3. Which is 4.67 inches. We just did that, right? Right here. What is that? 3. And what is 2h over 3? Was that 9.33? Did I get that right? Now, what about for this random point right here? Sigma Greg. How do we determine that? Well, how far is it from the bottom to sigma Greg? Inches? Half the height? How far is it from the bottom to the centroid? 4.67? So maybe it's 7 minus 4.67 inches. That is 2.33. Did I do that right? Yeah. So, that's all we got to do. So, sigma max for the top is MYT over I. So, 984,000 times 9.33 over 381.11, right? Thank you. Units. Write the units out. Inches, pounds, inches, inches to the fourth. Yeah, I made these numbers up, so we don't know what this value is going to be. But what is this going to be when we check this out? It'll be a pretty big number. Yeah.
All for 7 minus 4.6.
So, okay. All right. So, I said sigma Greg is 7 inches from the bottom, right? What? I put my name?
I just couldn't read it.
Oh.
Small. Font is very small. Small font.
That was funny. All right, so what are we getting for this?
9.36 PSI.
Have a second on that? There you go. So there's the stress. Okay. So what about the stress on the bottom? It's MYB over I. So same M over I. .67. Exactly, it should be, yeah. Because this, and the reason it's half is because we're dealing with the triangle. It's 2/3 height versus 1/3 height. So what do we get right here?
12,000.
And as for what I asked for, what did we say this was? It was 2.33? I just made it up. What do we get for this?
6,015.9.
Have a second on that. All right. So, to be clear, so to answer really sort of two questions at once, here's your stress profile, here's your centroid, so, and the stress profile looks something like that. This stress is 12,057.59. This stress is 24,089.36. And then I asked for a stress that was kind of like right here. That stress is 6,015.91. Very common in the world of engineering that you might be interested in stresses at not just at maximum stresses, but stresses along the cross section. For example, maybe I've welded an attachment right there and I want to see what the stresses are on the weld right there. Very reasonable question to ask. So if we want, we can say, here's our dimensions. 9.33. 6.7. 2.33. And let's make sure this is PSI. PSI. Stop. Stop with the inches. Sense? How about everybody else? That's actually really good practice for the exam. Pretty reasonable in the end, like 24 KSI, 12 KSI, that's pretty reasonable. This isn't Calc 3.
We haven't had Calc 3 yet.
You said partial. When you have Calc 3, you'll get it. Yes.
For like, so finding the maximum shear stress, it was like V max that you used, and then for the stress, like the 1-inch section, it was a different V value.
Yes.
But then for like, I think you used the same V max value. for like every,
I did?
I think.
Let me check the solution on that. I'll check and see. But I can tell you for this example, the idea is that for the section in question, we use the shear at the section in question. And then for Vmax, we use the absolute maximum magnitude across the board. Let me check the solution to homework 6. If there's an error, I'll get it fixed. So.
Because that one was like the distributed.
Yes, I think so. Yeah, it's been a while since I did that solution, so. Let me check, I'll check. Or I'll post it to Teams and we'll get it figured out. Any other questions? This is good stuff. I want to make sure that you're comfortable with all this. Would you like me to release you to the wonderful world of thermo and dynamics a little early?
Let's just do this for the rest of the day.
Do you have an emergency that you need us to solve?
Other questions? I'm going to pull the attendance up real quick for those of you that didn't get a chance to step it. I will see you on Thursday.